Okay.
Hi.
So, yeah, I'm David Maidman from Control Software Solutions, and today I'm going to talk a little bit about UML. So, we're going to be looking at why we'll try and model a software or a system, what UML is, how we might model software behavior, how we might model a software structure, and then interactions as well. I'll introduce you to a couple of UML tools, and we're going to have a look at the NI Goop development suite. However, there seems to be a problem with that on my machine at the moment, so we'll see how we get on with that. So just an advance warning, so it's not an exciting topic. There's nothing exciting about flowcharts. But I've found being able to model your system can be a really useful tool when you're either planning an architecture or overcoming a complex design task. In fact, the first time that I worked extensively with UML was on a project a few years ago, where it was quite a large project team, and there was the lead software engineer who didn't actually do any programming on the project. He was actually a text-based programmer, and he was used to struggle with the concepts when we used to talk about LabVIEW. So we had to find a way of being able to show him what we was implementing, and he kind of introduced UML, which some of it was very confusing for quite a while, because it wasn't really natural to me as a LabVIEW developer. So why do we want to model the system or the software? So it allows us to abstract away all the detail that might confuse our understanding. And it lets us put forward quite, we can present complex systems in quite a simple way. So you become very familiar with the type of diagrams that are in UML and what they mean, and you can show quite complex things very easily. So for modeling the systems, we use UML, which is a unified modeling language. So although it's very abstract, which makes it easy to describe these high level concepts, it's very precise and has a known notation that we follow. But because it's precise, it means that it can be machine readable as well. So we can go from some design, and then we can integrate that into our development environment. With LabVIEW, we can use a tool to import that. There's different levels of UML that we can do. So you could have something that's very informal, or you could have something that's kind of detailed in every kind of level. And all of that depends on the level of documentation that's required for the project. Or to try, either from a customer point of view or from a overcoming your technical challenges point of view. And then my kind of simple way of describing UML is that it's a standardized notation for modeling systems, representing different views of the systems using diagrams. So we don't try and show everything to someone all in one go. We just model different views, different things that we're trying to communicate, and all of those diagrams together are what create the model. And that could be very lightweight, or like I say, it could be something that's quite detailed, depending on the requirements of the project. So it doesn't have to be pages and pages of documentation. So I tend to will produce a document for an architectural blueprint, which obviously at that level it's quite abstract. But then for detailed design, unless the project requires for it, I prefer to work with sketches on a whiteboard. And often I'll make some sketch, we'll have a look, implement the code, and then photograph it and stick it in the project file. So as you can see here, I've got a very rough sketch of a component diagram, and then some other nonsense on the whiteboard as well. But that became part of our product design, and so capture it on a quick photograph and stick it in the file. Some projects you've got to report a lot more information to the customer, or if there's some kind of you need some kind of traceability for regulated industries, so you might then go and actually put all of that in a document. But if we don't need to document pages and pages of stuff, tend to try and avoid it. So I mentioned on the previous slide about the different degrees of UML. So we can work as a sketch, so as shown in the example there, as a blueprint, so where we're actually using a proper UML tool and capturing those diagrams in some kind of design document, or you can use it as a programming language. So the furthest I've taken that is in LabVIEW, where you've got the ability to import a file format generated from UML that's able to generate your class structures. But it is possible to take it even further than that. I don't think with LabVIEW at this stage. And the other reason that UML is described as a language is because it is you can generate your drawings and your diagrams in one language and in one tool, and then you can port them across to another tool, and you can port them into your development environment. So it's defined as a standard. So a lot of the stuff that we look at does kind of highlight its power regarding object-oriented programming, but I know not everybody works with object-oriented programming, especially in LabVIEW. But it works just as well with procedural or non-structured kind of programming as well. So it shouldn't be that you think you can't apply this because you don't work with object-oriented programming. So just before we get into the diagrams, there's two little bits of basic notation. First one, not very exciting. So anywhere on a UML diagram, you might see a note. So a note is just represented by a little piece of paper with a kind of dog-eared corner. And they can appear anywhere on a diagram, and they can be either attached to an element, or they can just be floating and not attached to anything, and they just give some additional information that you might want to get across to someone. So the other thing that's, and this is quite an important thing to understand, and that's stereotypes. So we use stereotypes to signify the use or intent of an element. So some elements, they can look quite common. You might want an element to be used in a certain way, and we can do this by applying a stereotype. So some stereotypes have default icons that you can use. But in general, if there isn't an icon, or even if there is, but you want to reduce the size on your block diagram, for example, you can just represent the stereotype by showing the stereotype name inside angle brackets like I've shown there. And there's lots of predefined ones that we can use, but you can define your own as long as it's you're able to communicate to your project team what the stereotype indicates. You can apply a stereotype. So you'll see these as we go through, and it will start to make a bit more sense what these are. But just two examples, so two different stereotypes represented in two ways. So as an icon and as a bracket stroke text kind of combination. So I'm sure everybody's seen the little stick man that's maybe used in use cases. So that is a stereotype. So that stereotype is for an actor, and on the top where I've shown the icon and the little stick man, this actor I've named administrator. It's just as acceptable to just draw a box and to label the stereotype as text, so actor, and then we can see that its name is administrator. The other type that I've shown here is an artifact. So an artifact is something that is deployed onto your system that is relevant to the system. So a configuration file, for example. And this can be represented by a box with a little document in the corner, and then the name. Or it can just be as a straightforward box. And sometimes you see different combinations of these as well. The reason that they are important is as I mentioned, it allows you to get across the intent of what you're trying to show. So if we was to consider a class diagram, which we'll look at later, so if you just draw a straightforward box and give it a name, then people would assume that that was the name of the class. But there's different ways that we can represent classes in a class diagram. So it might be a straightforward class. It might be, if someone's not using classes at all, it might be a LabVIEW library. It could be a cluster that you want to model as well, or it could be an interface, for example. So what we do is we can apply a stereotype. So with this straightforward box that I've shown with the name logger, the first box I've not given any indication as to what it is. So you might assume it's a class, you might assume it's a type defined cluster, but I've not told you what it is. So there's some assumption that needs to be made. With the other two, they're both called logger, but I've used a stereotype to give more information about how I intend someone to implement it. So one of them, I've got an object there, or a class that I've labeled as an interface. So that would be a special interface class. And then the one to the right, I've shown a logger as a LabVIEW library. So this is an example where people who might not be using object-oriented are probably still going to be working with LV-lib files. And you could still represent a lot of the diagrams that we show would apply to LabVIEW libraries as well. Okay, so there's two main types of diagram that we're going to look at. So behavioral diagrams and then structural diagrams. Then there is a third type, which is really a subset of behavioral diagrams, and that's interactions. And interactions tie together the two other types of diagram. So just as a first overview of behavioral diagrams. So these are used, obviously, as the name suggests, to model the system behavior. So this has a lot of use when you're trying to model functional requirements of the system, and the user is, or the end user is always going to be able to understand these. It's not kind of, doesn't get involved in objects or sequence diagrams or anything that's more programming minded. They are quite straightforward. So one type of behavioral diagram that I haven't shown is a use case diagram. I decided to leave that out of this presentation today. But then the first type, and probably the least exciting of anything really, is an activity diagram. So in UML, an activity diagram is its name for what everyone else would call a flowchart. So with UML, it's got some quite tightly defined notation on how we lay out our flowchart, for example. So what we have is we have a starting point and a final point. We have an action, which is usually just a white box. So the UML tool that I used today for this is giving them a nice yellow color for some reason. But we have a little box that says what the action is. And then we have a decision point. So most people will recognize this as a decision in a normal flowchart. However, in UML, it's also used as a merge point as well. You'll see how that looks when we look at a diagram. But then quite useful actually in UML is we have a fork and join. So the diamond shape, the decision and merge, allows us to show a conditional kind of branch. So the software can go one way or the other. what this solid bar does, the fork and join, it actually shows where the software can split and do parallel operations, which when we're writing our LabVIEW code can be quite useful. So just a little example. So this is purely for demonstration. So we've got our starting point here. So we've got an action, an activity called read sensor. And then I've got a decision point. So in range, and it's either is in range equals true or is in range equals false. So all I've said is, if it's not in range, set the alarm and then merge back into the main trunk. So this is where sometimes people question the relevance of this. I don't know why. In UML 1, they didn't have these merge nodes. You could go straight into where the code joins. I think it does make it cleaner. But yeah, so before you go on from your conditional branch, you go into a merge node. So then what we're doing is after the merge, we're resuming back on our path here, and then we get a fork. So the fork, this tells us that these two operations can run in parallel. So if we're thinking about a more simple activity diagram, we might have something that initializes our LabVIEW code, and then we fork, and we might have 4 or 5 processes in parallel, and then when they're all finished, we might then go back in and have our shutdown code. Here I've just shown 2 operations that can run in parallel, purely for example, so log data and update UI. So just a little bit, just a little note on the notation. So in the square brackets, so things on the wires in square brackets referred to as guards, and these are things that have to evaluate to true. So is in range equals true. That has to be true for us to be able to go this way. Is in range equals false has to evaluate to true for us to go that way, which perhaps I've realized was using the word false in there is not the best example. But that condition has to be true for the software to progress down that way. So moving on from activity diagrams, something that is probably a bit more useful and is relevant a bit to what Steve was talking about before is the state diagram. So state diagrams, they look very similar in a way to an activity diagram. There's slightly different notation that we can use, and we don't just have to. We don't only have to model state machines. Okay, so something like a process can be shown as a state machine that that we would traditionally think in LabVIEW as a loop with a case structure and so on in doing certain jobs. But it can also model the kind of internal state of an object itself or of a thing. So it doesn't have to be about a process loop. It doesn't have to be about a state machine as such. So I've got two examples to show. But just before that, I'll just go over the notation. So what we have, again, we have our initial state and final state, and then we have our actual states. Okay, so I've shown this as a composite state. So this has got a title and then it has some stuff. You can show it just as a simplified blob, the same as on an activity diagram. But what this composite state lets us do is put the state title, but then it also lets us have entry, do, and exit requirements. Now, all of these are optional. Okay, so you could just have on entry, or you could just have on exit, for example, or you might have all 3 or any combination. So the entry actions, these are the jobs that we execute when we enter the state. Okay, so just while I'm talking about this, just want to try and stop people thinking about the LabVIEW implementation, about seeing some kind of queue driven thing. Okay, so try and push that out of your mind. Okay, so when I show the next state diagram, hopefully it will make sense. But when we enter a specific state, we can do some jobs, and they might only have to be done when we enter the state. Then we can define do actions. So do actions is what it does during its normal kind of lifetime in that state, really, the thing that it does, its primary job. We can then also define exit actions. So these are the jobs that it does as it leaves the state. Okay, so these are all part of the state, entry, do, and exit, and we can define, we can define these as we need. The other bit of the other thing that we need to understand is the syntax that's used on the arrows that go between the states. Okay, so again, on these arrows, you can show all of these or none of these, or you can show any combination. What we basically have is the first thing that occurs is the trigger. So the trigger is the event that caused the transition. Okay, the thing that caused it to leave the state that it was in. Then we have the square brackets and we have a guard. So a guard is something that has to be true for that transition to be allowed. So for example, you might only go to run if system equals healthy. So trigger might be someone pushing start. So it might say, instead of trigger, we might say on push start. But then the guard that says whether that's allowed to happen or not might be system equals healthy. Okay. And then when you see a slash and a word, what that means is a behavior. So this is something that has to happen on the transition. So for example, if we consider this, if we have a, let's ignore the guard, let's just have a trigger slash behavior. So we might have on e-stop as our trigger. Okay, so on pressing e-stop, we might move to another state. Okay, but the behavior of the transition from wherever we're going to wherever we're going to, the behavior might be stop all outputs. Okay, so we can put some quite simple notation on that wire and give people quite a lot of information about what we want to happen. Okay, so I've got a simple example here. So this is the reason I wanted to try and push the LabVIEW implementation out of people's minds. So I've got here 4 states on this system. So this is going to be a process loop for, I don't know, reading and writing to or from some device. Okay, and I've identified 4 states. So initialize, disconnected, connected, and shut down. Okay, though they are the states, the abstract states that my system can be in. Okay, so it doesn't mean that on my block diagram code I'm going to have a case structure, 4 cases with for each of those states. Okay, that might be a way it's implemented, but it doesn't have to be. So what we can see here is, as we come into the initialized state, I've put a do action. So the do action is load configuration. So we can see here, it's going to come into initialize, we're going to load a configuration, and then it's going to go straight onto the disconnected state. So we might have somewhere some kind of status enum that tells us what the state is, or we could be publishing events as we come into each state. So the rest of the software, our user interface, knows what state the module is in. But it's quite reasonable to expect do load configuration. That might be a case in our kind of LabVIEW implementation. So in the disconnected state, I'm going to attempt to open a connection. So I'm going to do open connection. And there's 2 results from there. One is that there's an error, or there's a connection established. So if there's an error, I'm going to loop. I'm going to stay effectively. I'm going to stay in the disconnected state. So I don't really have to show this transition, but I wanted to show it to show the behavior. So I've said error is the trigger, and wait is the behavior. So before retrying, I'm going to wait some undefined time. But basically, I'm just going to do open connection until a connection is established, at which point I'm going to transition to the connected state. Now, when I'm in the connected state, I've defined 3 jobs that I'm going to do. I'm going to read data, write data, and check the connection. If at any point the connection is lost, I'm going to return to the disconnected state and attempt to open a connection again. If not, I'm just going to keep going round and round and round doing those jobs: read data, write data, check connection, and it will do that forever. The other thing, so then the two ways out of connected and disconnected is also, so I've got a trigger command, okay? So if we receive a command and that command equals shutdown, we progress to the shutdown state. Now, in the shutdown state, I'm going to stop the loop and then we're done and we're out of our process loop. Now, I could have put close connection as a entry requirement to shutdown. However, if you're coming from the disconnected, there is no open connection, so you don't need to close anything. So instead of putting it as an entry requirement, I decided to put it as a behavior on the transition between connected and shutdown. So if we're in the connected state and we receive a command, if that command equals shutdown, we will go to shutdown, but on the way, we will close the connection. Hopefully that makes sense. So by putting this this notation on the syntax on the transitions, you can give people quite a lot of information about how you want it to implement. So if we're just thinking about the LabVIEW implementation, so I might say, okay, I'm not going to have a case for initialized, disconnected, shutdown, or connected, but I might have a case for wait, open connection, close connection, stop loop, read, write, and check. Oh, and load configuration. So the states of the system do not always represent necessarily states in a like a case structure sense that we're perhaps used to programming in. And to try and get that across, rather than just show a kind of state machine, process loop type state machine, I've also modeled a object state. So if I've got a system that's monitoring pressure, for example, of a system, I might have an alarm states. Now, I might have a state called normal. Okay, so this actually comes from a real world application that I worked on recently, and we had an enum that said what the state was, and we needed to be able to maintain that and ensure that that was set correctly. So it had the states normal, which meant everything was healthy. Now, if an alarm is raised, we go to an unacknowledged alarm. So that is a state. So it's not a process loop, it's not doing anything, but that is a state that we can handle and we know, and that is the state of our object, let's say. In the unacknowledged state, someone could acknowledge the alarm. So it can go to acknowledged, and then it will sit there and it will wait. Okay. Or the alarm could get cleared while we're in there. So if the alarm's cleared, we'd go to an unacknowledged healthy state. Okay, unacknowledged return, I've called it. Now, if you're in an unacknowledged return and then the alarm comes back, you just go back to unacknowledged again. However, if you're in unacknowledged return and the user acknowledges it, you then go to the acknowledged state. Now, I've spotted a gremlin on my syntax here because I've put this as a trigger to say that we then go from acknowledged to normal on alarm cleared. But this alarm cleared is already been enacted there. So that should actually be inside square brackets to say if the alarm cleared condition has been met. Because in this instance, it won't have been. Down this path, it will have been. So we'll just put some square brackets around there. But it's a minor thing. So as behavioral things, there are two main tools really, or if we include use cases, three main tools. But it's a way of being able to kind of show how the software is going to behave, how it's going to fit the functional requirements. But it doesn't necessarily have a lot of design that someone can go in a way and implement. So the next thing we have is structural diagrams. So structural diagrams are used to model the things that make up the system. So the one that people probably most familiar with is class diagrams. So I've shown some very simple classes here. They don't actually have, I've not shown any methods or any data. And I've shown an interface that I've called data acquisition. And I've shown a data acquisition class, which realizes that or implements that interface. And I've said that our data acquisition has a scale associated with it. So it has a scale class. So I'll explain what all these different type of wires mean, but this is very similar. So I've got a data acquisition class, which I've shown in italics. I'll explain that in a second. And I've got two implementations of that, or two classes that inherit from it, shall I say. So a CDAC and maybe an Agilent kind of data acquisition device. So the reason that it's in italics is to tell us that that is an abstract class. So an abstract class is it's abstract if one or more methods are abstract. So it only requires one method to be abstract for the whole class to be abstract. And all abstract means is it means that some functionality will have to be overridden by the child classes in order for it to be usable. So I've already mentioned these different arrows. We've seen four kind of so far. We've got this closed arrowhead there with a solid line. We've got the closed arrowhead with a dotted line, and we've got this one with a diamond. Okay, so all of these have meanings. So if we see a dotted open arrow-headed thing, that's a dependency. So it just says that this library or this class works with this library or class, or this VI works with this VI, and so on. But we then have a straight line one, which is an association. So association is a dependency. It's just that it's a stronger dependency. So it says there's some more permanent relationship between these two things. Now, I tend to try and avoid using this one because I like to be able to see the direction of the dependency, because I like to ensure as well that the dependency is only one way. So library A is dependent on library B, but not the other way around. Otherwise, things get a bit of a mess. So these two diamond-headed ones, so the hollow one is aggregation. So aggregation is used when one object stores another object, but it's not necessarily the exclusive owner of that. It doesn't necessarily create it, or if it does, it might share it with someone else. The closed arrowhead, closed diamond composition, this shows when it is, that object that's created is purely part of that owning class. No one else sees it. No one else is involved in it. Now, from an implementation point of view, I tend to prefer to go for the open one, the aggregation, and that's so that we can have dependency injection, so that there's a looser coupling. It's not always possible, but when we come on to LabVIEW 2020 and people start using interfaces, this kind of concept of dependency injection will become a lot more kind of out there. But it's a weaker dependency. Then we've got an inheritance. So it used when one class is a type of another class and it extends that functionality. And then we've got a very similar one, which again is an inheritance, but it shows an implementation. And again, this is to do with interfaces. So I'll try not to talk too much about interfaces really. But as you can see, this arrow as we go down, we've got as you go down, you've got a much, much stronger class relationship. So between very weak at the top to very strong at the bottom. So just a kind of a summary slide to show, to break that down a little bit. We have these two top two. This is where class A, for example, uses class B. So it's a uses relationship. These two diamonds, it's a has relationship. So class A has a class B, an object of class B. Whereas these arrowheads, that's a is relationship. So class A is a type of class B, and it inherits from it. So hopefully that makes a little more sense than those long descriptions.
So David, we have a couple of questions. I mean, so one comment and a question really.
Go on.
So Danny is asking if you're saying that the class is on the left and then like an abstract class or something like that, I mean, so where you're pointing the arrows to, if I understand the question correctly, Danny.
This way.
Yeah, I always get mixed up which way the arrows go, whether it's how you read it arrow-wise.
Right, yep, that's a good question. So I should have picked up on that. So on this diagram here, so on this dotted one, the dependency is at the end of the arrowhead. So the dependent class, so the thing that uses the services of, so let's say class A uses the services of class B, the arrowhead would go to point to class B, okay? So the thing being used is at the end of the pointy thing, okay? Technical term there. Obviously on this one we don't have any direction, which is why I don't particularly like that. There is ways you can put notations on there to tell you who the parent is or whatever, but I tend to avoid this one. Now on these, the class at the end of the diamond, so the class where the diamond connects to, so if we go up one, that is the owner. So the data acquisition has the scale, an instance of the scale class. So this is the owner. Does that make sense on that one?
Yeah.
So inside that class, there might be a object called scale. So it has one of these. And then on these inheritance ones, basically the parent, so the base class or the interface is the class that's at the end of the arrow. But it is complicated, and there's more complication with arrows to come. Hopefully, when we see it in context, it will make a bit more sense. Am I okay to progress? Was there another question?
No, the other one was a comment on the circular dependencies by planning the dependencies, which is a good point.
Yeah. Okay. So on here, I've shown an interface. Again, I could have shown an abstract class. So at the moment, if I implement an interface in LabVIEW, actually what I'm doing is a purely abstract class. So all public methods, no data. So it's not really an interface. You can create it, won't do anything, but on a true interface, you shouldn't be able to create it. So it'll be interesting to see what comes out in 2020. But for the purpose of this diagram, this could be an interface or it could be a abstract class. Now here, so this is the realization. This is the class that inherits from and implements the one above. So we've got some data, and I'll explain the syntax of all of this on the next slide. We got data members, and then we got methods. And again, I've shown the scale. So I've shown the data that's in the scale, and I've shown the methods. So just to show the syntax of that, we've got, so I've taken the example of scale. So plus scale, and then in brackets, raw, double, double. Okay, so that's a whole big load of nonsense, really, unless you know what it means. So the bit at the beginning is the scope. Okay, so we should all be familiar with public and private scope. The next bit is the method name. So that's the sub-VI name. And then in the brackets, we can show the argument name and its data type. Now, all of this is, these bits are optional, really. So you don't have to necessarily show all of this information. You can cut it down to what's appropriate for what you're trying to communicate. So if I was doing a very, very rough thing, I might not show the arguments in there if I just wanted to show the relationships between these things. And then the bit that comes at the end is the return type. So scale is going to take a double of called raw, and it's going to return a double, which would probably be called scaled. That would make sense. So on the scope, so we've got 3 scopes I've shown. So public, private, protected. So these are all things that you can manage in your class or manage in your library. In libraries, I don't think you have protected, you have community, I think, which is a similar thing. But for a core thing, let's concentrate on public and private. So from our class diagrams, so all our class diagrams tell us they're basically the libraries we're going to implement. They don't tell us how they're used, really. So moving on from a class diagram, you can have an object diagram. So on an object diagram, we have, I've shown 4 objects here of 2 class types. So what I've done is I've shown a data acquisition object. So the name, the label to the right of the colon is the name of the class or library. Or in fact, you probably couldn't do a library with this. It's the name of the class. The one to the left is the instance name. So I have got an instance of the data acquisition library called thermocouple. Okay, so just one thing to be clear as well. So don't pick up on that it might not be a good design. I've shown them as separate things just for trying to communicate the concept, really. I've not gone for an elegant LabVIEW solution or anything here. So we've got a thermocouple. This is called thermocouple and it's of type data acquisition. And this is called pressure transducer and it's of type data acquisition. So the class that we had there, that single data acquisition class, I've created 2 instances of it. So an object is an instance of a class. Similarly, I've created 2 scales. So a temperature scale and a pressure scale, and they are both of type scale. Okay, so this could be an object. It could be just a type definition. That would depend how we'd represented it, perhaps with a stereotype. And what I'm saying here is I've got multiplicity there to show that one data acquisition thermocouple object has 1 scale, and you can have you can show one or many or many. Okay, so that's object diagram. So an object diagram is a snapshot of your objects in a moment of time. So don't. One thing I'll try and say is don't try and show everything, all of your potential objects. Okay, we should just try and model something that you're trying to communicate. So just the things that are relevant to what you're trying to explain. And so it might be that you have lots of scenarios that you explain rather than trying to have one big super model that tries to show everything. So keep your diagram as simple as you can. Just explain the thing that you're trying to get across.
So David, I mean, so how many more slides have you got?
I'm probably going to be 5 minutes over. Is that okay? Another 5 minutes?
Yeah. So there's one question which says, I mean, where do I start using a UML? I mean, do I start with a class diagram, use cases, or activity diagram, or maybe a state diagram? And what's your first point? I mean, when you start designing a project, I think that's what my understanding.
So, okay, right. So it depends what you're trying to show. Okay, so don't try and show your whole diagram, like your whole system in one diagram. So I would typically start. So the first part of the project where I'd introduce some UML is on a architecture diagram, and I tend to use the Cruchton's 4+1 architecture model, which recommends 4 views of the system. So each of those views is for a different person. So that's where we capture the blueprint of the system, really. So you have 4+1, so you get 4 views: logical, physical, which you'll see in a minute. Logical, physical, process, and development. Okay, so and then the fifth, the +1, is your use cases. So you've got to capture some use cases, which is your requirements for your customer, and then just sketch up the little bits that you need to represent. So it could well be that I start with an initial class diagram or some simple flowcharts, but I'll do all of that well before doing any interaction diagrams. So class diagrams and the kind of behavioural things would come first. Probably even behavioural quite early on, I'd say. But it depends what works for you.
Yeah, I mean, I generally start with use cases as a minimum, and then I'd have an activity diagram, and then from there, your interactions and also class diagrams and things like that. So, yeah, like you say, it's preference. I mean, so I like to see use cases to start with.
Yeah, and the activity diagram is very much it's very, very conceptual, isn't it? It doesn't go into any detailed design. It just gives you little flowcharts saying how it's going to behave, and you can do that very, very early on before you've even decided what objects you're going to be using.
Yep.
Yeah. So okay. So the next diagram I've shown here. So we are almost there. So I've shown the components. So again, this is a stereotype. It's a stereotype by its icon and by a label. Okay. Now it says component. Now I could change that to say library, or I could change that to say executable, or whatever. So a component is a collection of things, LabVIEW things, classes, sub-VIs, libraries, whatever, that together give you some dedicated role and responsibility in the system. So you might implement this as a LabVIEW library, as an executable, a DLL, or whatever. So in this example here, this is probably going to be each of these might be a library. And let's take data acquisition. The library, data acquisition library, LV-lib file, might have an interface class, a data acquisition class, might have a mock class, and it might have a scale, okay, and some other utility data types and so on. But they're all bundled up in something that makes them usable together. Now, what I've shown here is I've shown the relationship between these, the dependency. So my user interface is dependent on there being a controller. The controller is dependent on these two kind of service components, data acquisition and data logger. Okay. Now, I've just shown those as very general dependencies. So again, thinking about the interface notation. So as I said, at the moment, we do this with purely abstract classes. We can use this ball and socket notation. So a ball is a provided interface and a socket is a required interface. So my user interface requires a controller interface. So what that lets me do, so an interface, again, I'll try not to go too much into interfaces. An interface sets up a contract basically between the two components. And we said that we'd have an interface class. So this would refer to that interface class, and the user interface would be able to work with that class. And it doesn't care about what implementation. And we should be able to switch the implementation without any changes to user interface. So here, just because the ball doesn't fit in the socket, I've used the dependency arrow, and that's the correct direction. So the required interface is dependent on the provided interface. So just moving on from there, so we've got our deployment diagram. So this is how our software fits onto physical things. So this is something that I do quite early on as well, Shri. So you won't know all of the levels of what you're going to implement, but you'll be able to work out very, very top level what applications are going to sit on what targets. So I've done a very simple target with a typo there, but I'm showing an executable, but it's a component. So an executable application is going to sit on a Windows 10 PC, and it's dependent on an artifact, so a file called configuration. And then there's a association between the two, between an RT application, which is just sat on a Linux real-time controller. And you can build these up to be quite complex if you need, or they can be quite simple, but it gives someone a visual map of where the software elements are going to be. And then that lets you then break up your development. And it's something that you can picture very, very upfront. So there's just two more to go. So interaction diagrams, they're a type of behavioral diagram, but they tie the behavior to the structural elements that we've built. So the first type is a sequence diagram. So the first time I saw one of these presented to me from the text-based program, it blew my mind, and I just did not have a clue what was going on. Now, the way to picture it, these little blobs up here are objects. and the same notation. So this is the name of the class, and then the thing before the colon is the name of the instance. So I've got a user interface, and its name is main user interface. On controller, I've not got anything. That's because my controller is a singleton. I don't care what the instance is called. There's just one to work with. So what this does is this dotted line is the lifetime. It's called the lifetime of the object, and you can destroy it, so you can show that it disappears. This also works with libraries as well. This not destruction, but these lifetimes. These could be LabVIEW libraries. So we have here, and this is called the activation. So this is while that particular task is active. So here from the main user interface, I might send a message to the controller start. Okay. Now there is some relevance to the arrowhead, so I'll come on to that very quickly in a second. So the controller then sends a message to the pressure data acquisition module, says read. That does its read, scales the data. So this is a self call, and then it returns the data. The controller then checks it's in range, and then it does two jobs. So it logs the data, sending it to the data logger, and then it displays the data. Now, there's a subtle difference between the two arrowheads. So the open arrowhead is an asynchronous message. It's a fire and forget. So that could be on a LabVIEW implementation. We could be sending that command over a queue. Basically, we send it to the controller and we don't care. We're not going to wait for a response. We're going to carry on doing what we're doing, which is why this activation breaks there. A closed arrowhead means that it's a synchronous activity. So this might not be done over a queue at all. This pressure object might be inside the controller. And we basically talk to it, we read, it's a synchronous thing, it continues until we return the data. Okay, so something that is maybe a little easier to understand is a communication diagram, which is showing exactly the same information. Okay, it's just that we were more interested in the interaction between the modules, so we show the lines of communication, and then we can just use annotations to show the sequencing of the messages. So again, very quickly, so we've got main user interface, sends a start command to controller. Controller sends a message or interfaces here to say read, read, and then we scale. Then the controller checks the range, and then the controller sends a message to log the data. So yeah, so just as a final slide, so there's loads of tools available. One which I was going to show you is in LabVIEW, but it's not working very well on my system at the moment. It appears to be broken. The other ones are, so one that I've been using recently called GenMyModel is free, and it's a feature-rich, proper UML tool, and it can generate a file export, XMI, which should be able to be imported to LabVIEW. However, it doesn't appear to be working. Another tool, Enterprise Architect, is a very, very full and feature-rich program. It is a paid program. And then you don't have to use full UML tools. You can just use diagramming tools. So one that I know Shree hates is Visio. And but its UML stuff is not too bad, I find. You need to have Visio Professional. And all of the drawings that I've shown you today was done in one called Draw.io, just because, again, it's free, it's easy for people to pick up, and it's got some UML tools. But the GenMyModel is really quite good. If you create a data type, for example, it will show it as like a structure, and then for the rest of the model, that's then available as a return type. And it's it's really, really feature rich, and it's free as long as you're unless you want to share projects amongst the team, and then there's a paid for version, but it seems to be quite a good product.
All I'd say is Enterprise Architect is cheaper than Visio, so
okay, yeah, and you can get free trial version, and it just gets a longer and longer wait time on loading. So just as a very final slide, really, so I know I've overrun, so apologies for that, but just a couple of tips. So I've mentioned one already. Don't try and model everything in one diagram, because if you just overwhelm people, and the point is about trying to model simple scenarios. Okay, so in the sequence diagrams that I showed, you can have loops and conditional structures and so on as well, but you could quite easily just have model two different scenarios, a pass scenario and a fail scenario. Try not to put everything in one diagram, because you lose you make it too complex, and you lose that kind of the thing that it's good at, really. So consider who you're aiming at. So don't put information in that doesn't need to be there. And you could have different levels of diagram, depending whether it's a detailed design or an architectural overview. And as I said, as I do for a lot of our detailed design, I work with a whiteboard and just do quick sketches. And you can have two engineers in front of a whiteboard, and you can sketch out ideas quite quickly. If you want to formalize it later, then you can. But it's yeah, that's fine. So yeah, I mean, there's other diagrams that I've not been able to cover just because of time, but they are the core ones that kind of you can use to represent your kind of LabVIEW stuff. Is there any questions?